Good evening once again, my lovely viewers. It's been a long time coming, but here is another chemistry lecture. And what I'm going to cover today is a bit of acid-base chemistry. Just let me adjust that light a moment. See a bit better. There we go. And go through the general principles of the two common kinds of acids and bases that we think about, and how these impact on solutions. So, I'm going to start by drawing two molecules of water, because this is kind of the basis of acid-base chemistry. Right, now water itself is H2O, but in solution it kind of automatically does an acid-base thing. And what happens is one of the lone pairs on an oxygen will occasionally nick a hydrogen from an adjacent water molecule, and what that will do is it'll give us HO minus plus H3O plus. Now, the traditional kind of way of thinking is that an acid will increase the concentration of H3O plus or protons. We sometimes refer to that as H plus, but that's the actual species that occurs in acidic solutions, and bases will increase the concentration of OH minus. Now, that's the kind of essence of acid-base theory, but there's two kinds of acid and bases that we need to think about. Now these are Lewis acids and bases and Bronsted-Lowry acids and bases. Now, these are named after people. I'm guessing Lewis and Lowry are kind of Englishy names. Bronsted's drawn that badly as an O with a line through it. That's Swedish, I think. But yeah, these are basically just two ways of thinking about how acids and bases work, and they're not identical and they're not really interchangeable, but there are similarities. So I'm going to start with the Bronsted-Lowry one, because these are a bit easier to explain. Now, a Bronsted-Lowry, I'll just call it a Bl acid and a base. So a Bronsted-Lowry acid is defined as something which is a H plus donor. That means it will give out protons quite easily. And a Bronsted-Lowry base is a H plus acceptor. So basically, Bronsted-Lowry bases are pretty much anything with lone pairs, so that can be H2O, it can be HO minus, it can be an H3 with one pair on the nitrogen, water there. Most things with negative charges to a degree, but some anions. So for instance, if you take nitrate, sulfate, phosphate, etc., these don't like to take protons as much, which is why we're going to put these kind of over here, because if you have a proton attached to these are what make what are traditionally called the mineral acids. So for instance, HCl, HNO3, if I can actually write properly, H2SO4, H3PO4, etc. Those are kind of the traditional acids. If these are all either gases or liquids, if you chuck them in water, they'll give you an acidic solution because they give out protons. Bronsted-Lowry bases, traditional ones are hydroxide and ammonia, so you might have NaOH, move the camera, and an H3, which I've kind of listed there. Most of these are quite readily available compounds, and yeah, if you mix them with water, you'll either get acidic or a basic solution. And that's the kind of classical version of acids and bases from a GCSE chemistry point of view. Now, the next one that I want to think about are what are called Lewis acids and bases. These are a bit more complicated, but related. So, let's go with Lewis acid and a Lewis base. Now, the distinction here is that a Lewis acid, rather than being a proton donor, a Lewis acid is a lone pair acceptor. Now that means it'll have a vacant orbital which can accept a lone pair. And you can probably see where this is going. A Lewis base is a lone pair donor. Right, so now this is where there's kind of a bit of an overlap, because if we take our humble proton, H+, this is a lone pair acceptor. It will happily accept a lone pair from OH-, OH2, water, and H3 from ammonia to give H2O, H3O+, or NH4+. So there's how the standard proton is a Lewis acid and Bronsted-Lowry acid. A Lewis base, again, there's a fair amount of overlap between the Bronsted-Lowry and the Lewis acids and bases. Generally, anything that is a lone pair donor will also accept protons to a degree. So lone pair donors typically, again, you'd be talking about, the examples I've listed here. You can also think of basically lots of organic things that have got lone pairs will act as lone pair donors. You can also see things like Cl-, which has basically a chlorine with 1, 2, 3, 4 lone pairs around it, etc. Basically, yeah, most lone pair donors are Lewis bases. In some way or another, it depends how available the lone pairs are for bonding. Now, I'm just going to draw a line under this little bit, because things can get a little bit weird. Oops, zoom again, don't want to do that. Basically, if you have certain compounds, they can be acids, as in if you throw them in water, they will lower the pH, but they don't dish out any protons. Not directly, anyway. So, one of the classic examples of this is a compound called boric acid, which looks like this. Now, boron has 3 valence electrons, so it forms 3 bonds. Now, the thing to note about it is it has a vacant p orbital with nothing in it. So, what this can then do is go, we're in water now. It'll nick one of the lone pairs off a water molecule, and in the process it will form a compound which looks like this. Now, this water's just gained a positive charge. Water's not a huge fan of having a positive charge attached to it, especially not when it's attached to something else. So what it'll do is it will lose one of the protons. So indirectly, by kind of absorbing water and then pushing one of the protons away, we form this stable anion, which is called the tetrahydroxoborate anion. And then this will react with the water molecule to give us H3O+. Now, this is an equilibrium process, much like the dissociation of water, which I will come on to as a last-minute thing, I suppose. It's very much you're most likely going to find just the neutral form of this, but enough of this process happens to lower the pH of your solution. Now, as I mentioned, over the page, we end up with 2H2O gives us H3O plus plus OH minus. This is a bit more advanced. So, what you'll basically see, this is an equilibrium. It's not a favoured process. Basically, 1 in every 10 million water molecules will be in this state at any given time, and it's in a rapid state of flux. So there isn't really any way of predicting what's going to happen to any given molecule. But that is the number that comes to mind. And if you do some funky maths to this, the fraction is 10 to the minus 7. And you do some more maths to it, that gives you pH 7. So if you've got no other crap in it, that gives you the pH of neutral water, which means you've got equal amounts of those. And that's about it, really. If anybody has any questions on this, do post something in the comments. Please subscribe and like and yada yada. You know what to do with YouTube channels now. I'll be doing more content in the future, hopefully. And thank you for watching, and have a good evening. Goodbye.